Hi everyone, and welcome to our first video in Unit 1, our Integrated Math 3 video series. Once again, my name is Kyle Prince, and I'm your teacher for this lesson. So we're going to focus today on function types, and the various function types and their key characteristics. But first, before we do that, let's get into our warm-up for today. So if you would, take a few moments to see if you can solve these 6 problems. Keep in mind, mental math can be used for a lot of these, so try and do your best. All right, so let's start with number 1 here. 6 times negative 3 is negative 18. So you have negative 18 plus 7. So if you think about on your number line, you're at negative 18 and you're adding 7 to that, so you're going to go 7 in the positive direction. That's going to put you back at negative 11. All right, 2 to the 0. We talked about exponents last time in our last video, but that was when the exponent was a natural number. And 0 is not a natural number. It's considered an integer, it's considered a whole number, but it's not a natural number. So what happens when we have an exponent of 0? Well, let's take a look at a pattern and see if we can figure it out. So let's look at the powers of 2. 2 to the 4th is 16. That's 2 times 2 times 2 times 2. 2 cubed is 8. 2 squared is 4. 2 to the 1st is 2. And if you look at our pattern here, every time we go down a power in 2, we're dividing by 2. So what do you think would be the next if we divide it by 2 once more? Of course, it's going to be 2 to the 0 equals 1. And so 2 to the 0 is 1. And in fact, any number raised to 0, except for 0 itself, any number raised to 0 is 1. But let's think about it. If you have any number to the 3rd power, any number to the 2nd power, any number to the 1st power is going to be that number, right? So if you divide that number by itself, you're always going to get 1. So no matter what number you're working with, except for 0, of course. All right, so what is 15% of 20? Our next problem here. So 15% is something you might want to commonly do, maybe if you like to leave a 15% tip at maybe a restaurant or something. So let me give you some tips on 15%. So first of all, 15% is the same thing as 10% plus 5%. And so if you can calculate 10%, then you can quickly divide and calculate 5%. So 10% of 20 is, of course, 2. And then 5% of 20 would be half of that, which would be 1. Add those together and you get 3. So 15% of 20 is 3. Let me show you another way that's more applicable to any number, really. 15% is kind of special because it's 10 and 5 put together. One thing you can do with percents like this is take the numbers involved, so 1 and 5, so 15 here, and then 2 here, and don't worry about any trailing zeros at this point. Just take the numbers involved. So 15 times 2. 15 times 2 is 30. And then adjust the decimal place afterwards. So obviously 30 is too high, so move your decimal 1 place to the left and you get 3. Move it 1 more place and you get 0.3. And just think about which one makes sense. 3 is obviously going to be it. 0.3 is way too small to be 15% of something. If you think about 10%, you can always calculate 10% pretty quickly, and that can kind of be a way to help you think through that. Number 4 here, 3 and 5 really are one and the same. So let's just focus on number 5 here. Don't worry about number 4. So what number could we put in the box there? It's almost like solving an equation, but a different way to kind of look at it. So we can think about what number times 3 plus 2 equals 23. Here's where your number sense comes in. 3 times 7 is 21. So if you just kind of think about it, you might be able to get this. 3 times 7 is 21 plus 2 is 23. So 7 would make that statement true. What's the next number in the pattern below? looks like we're adding 8 each time. So it's a constant rate of change of 8 that's involved here. So you might think about like linear functions that you learned about back in integrated 1. So if we add 8 more, we're going to get 35. So 35 would be the next term there. So that's like your repeated addition, like I said, like arithmetic sequences and linear functions that you've learned about previously. All right, so let's go ahead and hop into some different function types. We're going to revisit linear functions here in just a moment, and some other function types that either you worked with previously, we're going to work with this year, or maybe even in future years. And so I really want you to see these though in context. So every single one of these function types, I'm going to show you a real life situation first, and then I'm going to give you a chance to kind of think about what function type would best model that particular situation. All right, so we're going to start with, and just bear with me with these videos here because it may take me a minute to get things going here. So for a couple of these videos, it's going to give you a 15-second clip. So we have 15 seconds along the x-axis, and along the y-axis we have the milliliters of water as it fills up. So it's going to be someone pouring water into this beaker here. And so I want you to think about what would the graph of the volume look like over time. Looks like she's pouring in at a pretty consistent rate here. So think about what function type might be most appropriate here. All right, and then let me show you the answer here. So as the water is going in, it's at a constant rate. And so the volume is increasing at a constant rate. And so this is a linear function. So it's an example of linear function. There's tons of other examples of linear functions in the real world. This is just one of those. But you can see a few things here. One, it's increasing at a constant rate, or what you called an integrated 1 slope. Let me pull it back to the graph there. So it's got a constant slope. Let me get rid of this. Okay, so we have a constant slope, and it's increasing. That's one of our keywords for today, is increasing. Throughout this whole entire video, the volume is increasing over time. The x-intercept is actually the same as the y-intercept here, which is 0, because it starts at a time of 0, but it also starts at a volume of 0. And so the x-intercept and y-intercept are both 0 in this case. So those are a few keywords that we're going to talk about throughout today, but there's our first example of a linear function. All right, let's move on to our next video here. This video describes the population in our world, and each little dot here on the screen represents 1 million people. And so I'm going to press play, and it's going to go from, it looks like we're about at 1475 right now, and it's going to go all the way to, I think, 2050. And so just think about what the graph would look like of the population over time. And listen closely and see what you think might be the case here. All right, so I wonder what you think. what kind of function do you think this is? If you watch the video and you see these dots popping up, it gets quicker in terms of the number of dots that are popping up at any point in time. And you can also hear it happening, right? It starts out slower, and then it gets quicker and quicker and quicker and quicker and quicker and quicker. And so as a result, we see that, let me create a little graph here. Over time, what's going to happen here is that we get a graph that looks something like this. Where it starts out small increases, and then it gets quicker and quicker and quicker and larger and larger and larger, slow in terms of its slope and rate of change. And so this is what we call an exponential function. So you may have guessed that coming in, but this is an example of an exponential function. A few things here. One is the y-intercept is here. It doesn't really have an x-intercept in this particular situation because it approaches this x-axis, but it never actually reaches it. So the minimum value here would actually be 0 because it doesn't go below or actually even reach 0. And then it doesn't have a maximum because it continues on forever and ever upward. So those are a couple other words that we're going to talk about more today, is minimum and maximum in terms of these graphs. So that's an exponential function. Let's move on to the next one. So this one, same as 2 videos ago, where we're looking at 15 seconds of time and what happens over those 15 seconds. We're actually measuring the guy's waist over these 15 seconds in terms of the height of his waist. So take a look at the video and see if you can think about what the graph would look like of his height of his waist over time. So his height started out about here of his waist. It goes down a little bit, slides down, and then actually increases just a little bit there at the end. So, so think about maybe what that graph would look like. Let's go ahead and look at the answer. So he's getting on the ladder, he's increasing at a constant rate. He goes across and then he sits down, and then he slides down, and then increases there at the end. So this is actually an example of what we call a piecewise function, where our function is defined by where you are on the x-axis. You may have talked about this back in integrated math 2, but let me show you a little bit. So from 0 to 1, and again we're talking about the x-axis here is how we're dividing this up. So from 0 to 1, we use this function here, which is y equals 3. Y equals 3 is just a horizontal line. And then from 1 to about 5.5, we're using this linear function. So the slope here is 0, we're not increasing or decreasing, and then all of a sudden we start increasing. All right, and it kind of levels off just a little bit. It looks like it's decreasing maybe a tiny bit there at the top. And then it decreases a lot, and maybe from, I don't know, 6.5 to maybe like 8. It's almost like an exponential, but an exponential decay. So the graph I showed you earlier was an exponential growth. So maybe an exponential decay might look something like that. And then, a flat graph here, maybe y equals 6.5. And then starting at like 11.8 or so, we have this sharp decrease. Maybe a linear function could model that. And then down here at the bottom, we almost have what looks like a quadratic at that point. And so from here to here on the x-axis, it might be defined by this quadratic, and then the last piece here also might be a little bit of or at least half of a quadratic. And so a piecewise function is one that's defined in pieces based on where you are on the x-axis. So this section corresponds or follows this idea of this particular function. Between here and here follows the rules of this particular function, and so on. And so let's actually look at another type of piecewise function in our next video. So in this particular video, we're gonna have a car driving by, and I want you to think about the quantity that's represented by the car's distance from the camera. So think about how the car's distance from the camera changes over time. So the car is really, really, really far away, and then it's driving, we'll assume at a constant rate. It goes by the camera, and then it continues past and away from the camera at a constant rate. So let's think about what that graph would look like. We'll go back to here. We'll plot it on the same XY axis here. So if you think about time at 0 seconds, so right when I started the video was it 0 seconds, we'll say. The car is really, really far away. So maybe right here. And then as the video went on, the car got closer and closer and closer to the camera at a constant rate. And so it might look something like that. And then right when it crossed right by the camera, it was at its closest point. And I'm saying 0 here, but really it didn't hit the camera. But we'll say it was really, really close to the camera. And then as it passed the camera, it's still going at a constant rate. It started getting further and further away from the camera. So something like that. And this is what we call an absolute value function. It is actually a type of piecewise function because it's defined in 2 pieces. This piece here and this piece here. This piece here has a slope of, we'll call it normally -1. In our video, it was whatever speed he was going, he or she was going. And then here we have the positive of that same slope, which again is typically 1, but in this case, whatever speed. A couple things to note here. We have a y-intercept at the top there. That's our initial distance from the camera. So a lot of times y-intercepts means the initial value, especially when you're talking about time. And then the x-intercept down here, what does that represent? That represents the time at which the car was closest to the camera as it was going to be. In fact, we're saying there's 0 feet or whatever the units are away from the camera, almost as if it hits the camera. So that's what that x-intercept represents. So we're decreasing, and then all of a sudden we're increasing. This point right here is actually what we call a minimum. Now this is actually the absolute minimum because it's the overall minimum of the entire function. I'm going to put arrows here because these functions continue forever and ever in both directions. Now in terms of our context, it would start at 0 and go onward until the video stops, but the graph itself would go on forever and ever. So those are some characteristics that I wanted you to point out here: x-intercept, y-intercept, minimum value, as well as increasing and decreasing. All right, so that's actually our last video for right now. And so what I want to make sure we do is revisit our goal for today. So our goal for today was to describe and use key features of graphs to understand real-world situations. And also, I want to make sure that we recognize various function types and connect them to real-world situations. So we're thinking about characteristics as well as function types in these situations. All right, so I also wanted you to think about filling up these containers. I've matched them up for you already, but I want you to think about pouring water into these containers. If you pour in at a constant rate into these containers over here, how would the height of the water change as you pour that water in? And so think about how these are each connected to these graphs here. So for instance, let's take a look at that eye here. So it starts out pretty narrow. So that means the water, as it goes in, it's going to rise a lot quicker because it's narrow. The wider it is, the slower the height is going to change. So it starts out really increasing pretty quickly. And then as it gets wider, it's going to slow, 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 slow. But then it's going to get skinnier again, so it's going to go quicker, 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 quicker. And then very quick here at the top because it's pretty skinny there. So again, it starts out pretty quick, but then it gets slower over time, or over the increase of volume. Slower, 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 and then it starts to increase, 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 increase. And so that's how that one connects. But I really want you to encourage you to think through the rest of these and how those graphs model these situations. You can see some piecewise functions in here, like this one here, which actually doesn't match a container, but it starts out at one slope, and then from here onward, it follows a different function. So you can see that there. This one looks pretty similar to an exponential growth function. And there are some other ones as well, but I really want you to think through how they connect, because that gets us at our goal that we talked about a second ago of connecting those characteristics to their graphs. All right, so some things we've talked about today. We've talked about increasing, decreasing, constant rate. We've talked about maximum and minimum. Relative maxes and mins, let me make sure we understand that too. So let's say we've got a graph here, and I know that maybe you haven't seen a graph like this before, but let's just take this graph for example. This right here, you might think is a minimum, but it's not. This point right here is not the overall what we call absolute minimum, because the function goes below that over here. But what we call this one, maybe like a trough or whatever you want to call it, a valley, is a relative minimum, because it's the minimum in this particular zone, but it's not the overall minimum of the entire function. All right, just like this one here, this like crest or hill or whatever you want to call it, is called a relative max. Because it's not the overall max, because it goes higher than that over here, but in this region, it is the relative max. So some keywords there. Let me go ahead and draw a set of axes here so we can develop some other words to make these connections here. So I'm going to circle these in red. So we have the relative max, the relative min, let's see, it's increasing. This part of the graph is increasing. Later we're going to talk about actually describing them with the x values that we're at currently. So for these x values, it's increasing. For these x values in between here and here, it's decreasing. And then for here onward, the graph is increasing. So think about increasing and decreasing, maxes and mins. This graph does not have an absolute max or min, because it goes down forever and ever and up forever and ever. So it would be infinity, if you think about it that way. Axis of symmetry, we're going to talk about that here in a minute. And then zeros, which can also be x-intercepts or roots. I think you know what x-intercepts are, but they can also be referred to as zeros or roots. And that is these points right here. These are x-intercepts, zeros, or roots are kind of interchangeable. And so those are x-intercepts. And then lastly, we have y-intercept, which is this point right here. And a y-intercept is actually a point. It's not like the y value that it crosses, it's the point itself. Just like all these are points. So I wouldn't just say the x-intercept here, for example, is like -6. I would say it's -6, 0. Whereas this one, I wouldn't say the y-intercept is -1. I would say it was 0, -1 is that point there. I'll always look out for the scale and know your units. You can think that there's some differences in graphs, or maybe you think they're the same because of the scale is different. So really pay attention to that y-axis and the scale that's involved with your graphs, because they might look the same overall shape, but yet the scale is totally different. So be on the lookout for that. Okay, so overall, here are some different function types and different characteristics that go along with them. So we have linear functions, which we talked about back in integrated 1. So we can have a positive slope, we can have a negative slope. Again, this one's increasing, this one's decreasing. We can have an exponential growth or an exponential decay. Again, one is increasing, one is decreasing. So familiarize yourself with those terms. We have absolute value graphs. This one is what we call concave up, meaning it's opening upward. And then this one is opening downward, so concave down. So this one here has a minimum, whereas this one has an absolute maximum. And so keep those terms in mind. Also, absolute value graphs are symmetric. And so one thing we want to talk about with these graphs is what line divides it in half. So is what we call the axis of symmetry. So if you were to flip it across that or rotate about that axis of symmetry, it would land on itself. So for this particular graph here down here, move it over just a little bit. That would be your axis of symmetry. So that's a term that you're going to see pop up. Hopefully you saw it last year a little bit. That's going to be a term that you see popping up here. So if we were to fold this over, it land on itself. So absolute value graphs are symmetric. So are, as you talked about last year, quadratics. So in this case, x equals 0, this y-intercept here, or sorry, y-axis here, is the axis of symmetry. So these two, absolute value and quadratic, have a lot in common in terms of symmetry. Then we have piecewise functions. So we have piecewise functions in general, which are defined in pieces based on where you are on the x-axis. And then one particular piecewise function that sometimes separated out is something called a step function. Basically, if you input any x value, the output is the rounded value of that number. So if I have an x value of 2.13, well, it would round to 2, right? So it would be up here. So all these values in here round to 2. All these values along here on the x-axis round to 3, and so on. So you see these steps that form, and that's what we call a step function. So I hope that kind of gives you an idea of not only the function types, but also the common characteristics that we see throughout these function types. And in our next video, we're going to dive into quadratics a little bit more, which, as I said last time, is going to be our bridge into integrated 3 with polynomial functions. So I hope this was a good recap of our function types and the characteristics that go along with them. And at this time, I'll say goodbye, and we'll see you next time.